All right, let's talk about DFT Analysis. We have a full question here. Let's look at the number 4 first. We will first go through the process of calculate 4-point DFT. Let's look at the GN first. So GN is 4 points in the time domain. And I should show you the process. So we have 4 points in the time domain. Okay, so we use lowercase x n here. So you can say that's x n. When n equals to 0, then we got this one equal to 1. That's the first bit, okay? And 1 equal to 2, that's the second. So n is the index. Oh, sorry. This is 2. We got 0. Lowercase x 3. We got a 1. Okay, so just time domain numbers. The task is to calculate a capital xk. K is the index for the DFT. All right, so we're gonna looking for, so 4 points in time domain gives you 4 points in the frequency domain. All right, so we're gonna do this all the way to capital X3, so 4 points. All right, we just plug in those equations. So if you look at the equation, we have this lowercase n, which we're gonna sum all the n equal to 0, 1, 2, because we have 4 points here, so capital N equal to 4, right? So we have a 4 term. Each term have the lowercase xn, which is one of this, and multiply e to the order of negative j 2 pi k here, okay? K is the index for the capital X, all right? You can see that for first term, k gonna equal to 0, right? And capital N is a fixed number. N is another, is this n looping around, okay? Let's see the example. First, plug in all the numbers. Capital X and capital X0, k equal to 0 here, capital N equal to 4, lowercase n looping from 0 all the way to 3. So first term, lowercase n equal to 0. Okay, so this one, k equal to 0. Then e to the order of j 2 pi, k is 0, 0 or 4, multiply lowercase n 0. So this whole term is 1. So the first one we got is lowercase x0. The second one is x1, e to the order of this one, because this k is 0 again, so this is 1. And if you plug in numbers, you can see n equal to 3, n equal to 4, n equal to 2, n equal to 3. This e to the order of something always equal to 1. So what we left is x1, 2, and 3. 4 term of them. So x0 is this one, 2, 3, and 4. So 4 term. 1, 2, 0, 1 plus together is 4. So capital capital X0 is equal to 4. That's the first term. We got it. And for the second one, a similar thing here. You just plug in number, and you will find this first term, e to the order of j 2 pi 1 over 4, 0. So it's 0 degree. So this is the plot for e to the order of negative j 2 pi multiply with something, okay? Multiply with something. If this is 0, then that's this one. This one equal to a 1, okay? And the second one you can see is negative 1/4, a quarter of this 2 pi, a quarter of 2 pi and negative, that means let's go this way. All right, that's the second one. That's the second one. That's why this is a negative j. Okay, this term is negative j. And you can see the next one is negative 1. This one is negative 1. And next one is positive j. So this is a positive j. Okay. So we can multiply everything together. That's first lowercase 0, lowercase 1 multiplied negative j. This is lowercase 2, and this is a lowercase 3. Okay, 1, 2, 0, 1, still that 4 piece. Okay. Then we got all the term together. So the second one, capital X1 equals to 1 minus j. You got that. Okay. Same thing for here. So you can see the pattern here. That is because the the numerator on the top here is capital N, so it's always before. This is always before. Okay, but in this one we have another term which is a 2 here. This is the k. Okay, this is the k. So we always have k. So the first one is 0. So the first term is 0. So this whole thing is equal to a 1. And the second term here is half pi, half 2 pi. Okay, negative half 2 pi is this one. So it's negative 1. And this one is, so this is half pi, half 2 pi. This is 2, so it's a whole 2 pi. Okay, is it go around the clock. Okay, so go around the clock, that gives you a 1. Okay, but it doesn't matter because it's multiplied with a 0, right? And this one is go around the clock. Okay, so this is negative 1 again. So it's 1 minus a 2 plus a 0 and minus a 1 here equal to negative 2. Okay, so the second bit is negative 2. So capital X 2 is negative 2. Last one. Do we have X? Oh, sorry. 0, 1, 2. Yeah, we should have a 3. Okay, let's do it together for the 3. So capital X3, that equals to lowercase 0 multiply e to the order of negative j 2 pi. This is n, so there's a 4 on top. That's 3. Multiply with the first term and plus a sorry, this one will be the number 1 and e to the order of j 2 pi 3 over 4 multiply with a 1. Okay, and the third term x 2 e to the order negative j 2 pi 3 over 4 multiply with a 2. We don't really need to care about this term because this x2 always equal to 0. So this term is always gone. But we just write down there. So this one is negative j 2 pi 3 over 4 multiply with 3. Okay, this time is go around the clock. This term equal to a 1 as always. And this is always a 3/4 of 2 pi. So this is 1/4, 2/4, 3/4 of 2 pi. So that is 1 of this. Okay, and this gives us a positive j, right? So this one is positive j. And how about this one? This one, another 3/4, 1/4, 2/4, 3/4. This one's supposed to be a negative 1, but it doesn't matter. And 1/4, 2/4, and 3/4 give you a negative j here. All right. So if you still remember all these x, so for the first one, x0 is 1. 1 multiplied with 1 plus a x1 is 2 multiply with a j plus a 0 multiplied with a negative 1 plus a, the last bit is also 1 multiplied with a negative j. Okay, so let's see, this is 1 plus 2j plus 0 plus a negative j. So is 1 minus j. Sorry, 1 plus j, right? 2j minus 1 is a plus. So 1 plus j. Okay, let's come up here. So there's last term. Number 3 equals to 1 plus j. Okay, we are finding a very interesting thing here, which is x1 equals to x3 complex conjugate. Okay, let me write down here. So capital 1 equals to complex conjugate of 3. Okay, we're going to prove that in the first question. That's something we want to do. All right, so if you got all these 4 numbers, that means you finished the DFT. Okay, I will leave this HN. So we got a capital, we just got the capital G, what's that called? GK. Okay, so you do a DFT here. So I will leave this one for you to try. Now let's look at this one. So explain how the symmetry property of DFT can be used to significantly reduce calculation required for the performance of DFT. Okay, so this one, the symmetry property says this. If your input is all real, that means the lowercase x 1, 2, and 3, blah blah blah, they are real. They are real numbers, like these ones. They are real numbers. Then your capital K gonna equals to the complex conjugate x and minus k. All right. In our case, in this case, n just equals to 4. So what has happened is we will say x0, if k equal to 0, then this is equal to complex 4 minus 0, which is a 4. We don't really have that. The largest one we have is a 3, right? So we didn't find a exactly same one. But 1, when k equal to 1, then capital X1 gonna equals to 4 minus 1, which is a capital X3. All right. Sorry, I forgot the complex conjugate here. Okay, that's why G1 is 1 minus J. Then the J3 was 1 plus J. Okay, complex conjugate. That's how it works. Okay, you can see that if you have a more number of n is larger number, then you can actually save half of the calculation. Okay, you just do the first half, then you can do the complex conjugate for the second half, so you don't need to calculate that. Okay, for the second question, okay, maybe move it down a little bit. So for the second question, which 2 parameters are considered when setting the resolution for DFT? Okay, we have a equation, I think Owen mentioned this during the class, which is the K over capital N equals to FA over FS. So this FA is the spark room in the frequency domain. So if we move terms, then we got this lowercase k Fs over N equals to FA. Okay, so K is, you remember that, GK. Okay, so we have the capital G 1, 2, 3 when we do the calculation here. So between these two, between k plus 1 and k, between this is actually fs over n. Okay, fs over n equals to delta fa. Okay, so that means the two spectrum, the distance between these two spectrum. So if you want a higher resolution, you want to take more more samples. Okay, fs you have to set is at twice of the maximum frequency in your signal. So probably this one you can't do much, but if you want to have a higher resolution, you can take more sample. Okay, that's the second question. So last one is the third question. Okay, we try to compute endpoint DFT of the length n sequence. That's a general form. So xn is a general form instead of a point, but that's okay if you plug in all the numbers. You know, if r has to be a constant number, n is a variable. If you plus all the numbers, that give you exactly the same thing like this, but just different numbers. Okay. All right, let's try this one. So for question 3, first we want to use the trigonomical identity to extend this one. So this cosine 2 pi Rn lowercase n over capital N, lowercase n over capital N, can be rewrite like this. It's equals to so this x over n lowercase n equals to 1/2 e to the order of j 2 pi Rn over capital N plus a e negative j 2 pi Rn over capital N. Okay, so you can see that there's some similarity to the previous question. Okay, well, we're gonna do this. So if we have this, we want to do a DFT of that, right? Endpoint DFT. So we got a capital X K, right? That's what we gonna have. Then this one is sum of n equal to 0 up to n minus 1, and we just put this lowercase xn here, e to the order of negative j 2 pi, and that is k over n. Sorry, there's capital N here, and multiply with a lowercase n. Okay, because we got this here, so we can put that one into xn. So this capital Xn, probably I need a larger space here. So this one gonna equals to the sum of n equal to 0, n minus 1. Let me pause here and write everything down. Okay, what I did is just plug in all this big thing into this one. Then we can actually make this one multiply with this one, and another one is half of this one multiply with this one as well. Okay, so let's do that. So this one equals to same sum and n minus 1 and 1/2, okay, of this e to the order of j 2 pi, because this is a negative sign here, all right, and they always have n, so we have n on the denominator. We have this r minus k, r minus that k on top, and they all multiply with a n. All right, so I put a brackets up here. Okay, put a brackets here, And I just don't need this bracket, I think. And we're gonna plus, okay, another term, another sum sign of n equal to 0 all the way to this term, another half e to the order of j2 pi. In this case is r plus k over capital N, lowercase n. All right, that's these two terms we're gonna look at. Okay, that's the two terms. And let's just look at this term first. Okay, look at this term first. I'm gonna put down here, sorry, this whole term. So this is 1/2 of this one. Let me not copy all of them. Okay, just look at this term. Okay, just look at this term. What we're gonna do is for analyze it for r equal to k. Okay, there are two cases when r equal to k and r is not equal to k. When r equal to k, this whole term becomes the sum of this n minus 1. There is 1/2, okay, and e to the order of, because this is 0, right? So j2 pi multiply with 0, and this whole thing is equal to 1, okay? And you sum n piece of 1, okay? So it's actually equals to 1/2 of 1 plus 1 plus 1 all the way. In total, there are n number of 1s, okay? So that's gonna be gonna be n, right? So in total is half n over 2, okay? Half of the n for the first term. And for the second term, change color. For this term, oh, sorry. Before I go to that, I only looking at a one special case, r equal to k, right? Because when we looping around k, but k can be any number. There will be a condition when r equal to k. R is a constant, right? When r is not equal to k, when r is not equal to k, what happened? That is 1/2, okay, n equal to 0, capital N minus 1, e to the order of j 2 pi. This is a number, right? For k equal to a certain number, right? So this is a constant. For example, because this one equals to capital X k, right? Let's say, give any example here. Let me rows over. So say k equal to 2, for example, and r maybe equal to 1 for 3 maybe. When r equal to 3, so this one becomes a number. Okay, let me write like this. So r minus k over n. Okay, that's that one. So what is this? If k equal to 2 and r equal to 3, you can see that e to the order of j 2 pi, that's 1. N, for example, n equal to 4. Okay, like that. And this is lowercase n, right? We're gonna sum this whole thing up, start from 0 all the way to 3, right? Because n equals 1. So what is this? We did the DFT up here, so we know this is actually a lot of phasor. So a quarter from 1k equal to 0, 1, 2, and 3, right? So n equal to 0, that's actually 0. So let me change the color here. So 1n, n equal to 0, then you got this one, n equal to 1. Okay, this is not negative, so this is positive. N equal to 1, we go this way, okay? A quarter of 2 pi. then another quarter of 2 pi, another quarter of 2 pi. And what you need to do is you need to sum them all together. All right. So for 4 of them summed together, you can see this is actually equal to 0. All right. So for r is not equal to k, this whole thing equal to 0. We can have another example. For example, if your capital N, this is n equal to 4, your capital N equal to 3. If your capital N equal to 3, then you have this one equal to 0, 0 as always. Another one is positive a quarter of 2 pi, sorry, 1/3 of 2 pi, something like this. And you have another 2/3 of 2 pi, have something like this. So you split into 3 parts, and this 2 actually can add it up. If you add this 2 together, so all 3 together, they cancel each other, is still equal to 0, no matter how much is n. Okay, so in short, this whole thing, this first term, when r equal to k, that one equals to a half n. Okay, when r is not equal to k, then this term equal to a 0. Okay. All right. So what about this second term? So you can see here, the second term here. Maybe let me copy paste it to a different place. So for the second term, okay, for the second term we have here when r equal to k. Okay, when r equal to k, this is just another number. Okay, so you just doing a different spinning circle. Okay, there's just multiple spinning, but it's all being divided by n. So it will be cancel each other. So this whole thing, when no matter r equal to k or r not equal to k, this whole thing is equal to 0. Okay, but this is equal to 0. This let me do this. Not equal to k. The change color. The capital X k gonna equal to 0, but when r equal to negative k here, okay, when k equal to negative k, all right, so this becomes 0. Then is the capital X k becomes a bunch of 1 summed together again. Okay, so there is a 1/2, right? So this is a half n as well. Okay, so that's actually proof the conclusion. If r equal to k, then we have half n, and one okay, here is a bit different. So what we got so far is k equal to r, and k equal to negative r. Then we have this conclusion, right? But what about this? So if you think about this one, we start from 0, and here is the n units we took, okay, and here is the half n we have, okay, and n minus r, okay, here is the n minus r is actually just equals to a negative r, because it's gonna repeat itself. Okay, it's symmetrical to each other. So n minus r is actually just negative r. So we proved that is true. Okay, so that's all for this week.